In this statistics section, we will be discussing estimating a population mean. We will again be talking about confidence intervals, so you are going to see a lot of the same information that we just had in the last section when we talked about estimating a proportion, population proportion. So you will find a lot of this to be very repetitive, and if you've watched the previous one, you could probably skip through a lot of this and just focus on the stuff that is specific for means. Okay, so let's get started. All right, so when we are finding a confidence interval for estimating a population mean with a standard deviation that is not known, that's where we're going to start first. Okay, if I don't know. So all I'm going to know is the sample standard deviation. I'm not going to know the actual population standard deviation. All right, couple of important requirements. Again, must be a simple random sample. And we're going to have to either know that the population is normally distributed, or we're going to have to know that that sample size is greater than 30, one or the other. You're going to find that the formats are very similar. Rather than P and P hat, we're going to have X bar and mu, right? Mu being our population mean, and then X bar being our sample, our point estimate. So a lot of this is going to look very simple. Now, if you do not know the standard deviation of the population, you must use, instead of a Z distribution, you're going to use what's called a T distribution. And a T distribution is very, very similar to a Z, and it is used when we have very small samples. This was actually developed by an employee at Guinness in the UK. So just in case you're wondering if alcohol has ever served a positive purpose, it has. It has given us this lovely T distribution. And we always use it when we have very small samples. And this also uses what's called a degree of freedom. Now, when you're looking up the T chart, there's a chart for these, just like there's a chart for the Z's, same thing. They're going to look a little bit different though. We have to use what's called degrees of freedom, and there's always one less degree of freedom than there is the sample size. So if the sample size is 20, then our degrees of freedom would be 19. All right, and the confidence intervals are going to be done exactly the same as they were before. So that's the good news. Like there's going to be very little difference in what you see. The critical values, however, are just going to be those T values instead of the Z values. So we will talk about that chart, so that will be a little bit different. The degrees of freedom, again, is always one less than the sample size, so that's important. As you get to much larger sample sizes, the degrees of freedom won't matter. You'll find that there's very little difference. So again, when you're rounding, please make sure that you always use the original data all the way through until you get to the end and then do the rounding. And when you're using the summary statistics, make sure that you round the confidence interval limits to the same number of decimal places that you used for your sample statistics. So if the mean used one decimal place, then your answer would have one decimal place. All right, when we're using the T distribution, this is how we find the T, just like the Z. We're going to do X bar minus mu. And then again, notice like from that central limit theorem, okay, that comes back again. Okay, so that is adjusting for that small sample size, that S divided by the square root of N. All right, degrees of freedom, again, is just one less than our sample size, and that's going to help us look up things on the chart. So you have to be able to recognize your degrees of freedom because that's going to help us on the charts. And again, those critical values can be found using technology as well, not just tables. Obviously, the technology is going to give you a better estimate than the table will, but the table is still accurate, so keep that in mind. And I just have this nice little drawing to show you. So the normal distribution is in green. The student T distribution of n equals 3 is in the blue. Notice it looks kind of like the same, but it's a little bit shorter, and then the ends are a little bit taller. But then as the size grows, so say your sample size is 12, and notice it's fitting closer and closer. It's much closer to the green on both in the middle and on the ends. So as that n grows, it will get closer and closer and closer to fitting that standard normal distribution. So this is why I like the T, because it's very, very similar to the standard Z distribution. Again, it is also, they're generally symmetric, bell-shaped, just a little bit more variability, that's all. The student T distribution also has a mean of T equals 0, just like the normal distribution had a Z of 0. The standard deviation of the student distribution varies with the sample size. So unlike the standard normal always had standard deviation equal to 1, okay, the t distribution will vary from sample size to sample size. And as n gets larger, the t distribution gets much, much closer to that standard normal distribution that I showed you in the last picture. So just to give you a couple things. All right, so when you're constructing these confidence intervals from you, number one, verify that the requirements are satisfied, right? Like either you have the population, okay, you got to have the simple random sample, number one, and then number two, it either has to be normally distributed or you have to have a sample size greater than 30. If the standard deviation of the population is not known, and that is usually the case, I will put that in there, you're going to have to use that t distribution table and use the n-1 degrees of freedom, and we will talk about that. Evaluate your margin of error using this formula, which should look very similar. You have your critical value, and then here is your standard deviation, but it is being, justified, to get rid of that bias. All right, then number 4, we're going to use that error to create our confidence interval, and you can, again, the 3 different ways you can write it. And then number 5, make sure you're rounding correctly. Rounding should be done to the same number of decimal places as the original data. All right, so first let's just talk about how do we find these critical values. So if we find the critical value of t of alpha over 2 corresponds to 95% confidence interval, given that the sample size is n equals 6. Okay, so first of all, if n equals 6, we know our degrees of freedom is equal to 5, right? It's always one less. And if we want a 95% confidence interval, remember, when we look at that distribution, we're going to want 0.025% up here and 0.025% down here, right? 95%, we want the 2.5% on the high end and 2.5% on the low end. All right, so then I'm going to have to go to my t distribution table. And this is where you got to make sure you look it up correctly. You want to look up. We want to go to the column that has our alpha of 0.05, right? Because that's what we knew, right? We had an alpha of 0.05. We're going to go to that column. So I'm going to label that column. So you're going to go to that column. You're going to make sure that you are also looking at the area in 2 tails. So that's very important as well. Make sure you're in the correct column that says, if you want to use the 1 column, right? If you want the 1 tail, make sure you're looking up your alpha of 0.025. They should give you exactly the same number, but it's important that you keep that in mind. All right, so then I'm going to go look that up in my chart, and my t for 0.025 turns out to be 2.571. So make sure you go look in your chart and see if you find the exact same one, and make sure that you're looking at the t student distribution chart. Very important. So that is going to be my critical value for this problem. So I'm not going to ask you to memorize these because I think just looking them up each time that you need them is probably the most appropriate. All right, so let's go put this into practice and find some confidence intervals. All right, so let's say that we were talking about Reese's Peanut Butter Cup miniatures. Package has 38 cups, and the package label states that the total weight is 12 ounces. Well, if I take 12 ounces and I divide it, which is 340.2 grams, and I'm going to divide that by the 38 cups. That means that the mean weight, so the mean weight, oops, that's supposed to be an underline. My highlighter's not working. Here we go. Mean weight of this, right? I'm going to take the 340.2 grams, I'm going to divide it by the 38 cups, and that should be the mean weight per cup. All right, so I'm going to take a sample, and I'm going to weigh each of those peanut butter miniature cups. And these are the numbers that I got when I weighed them. Okay, use the listed sample data to find the point estimate of the mean weight of Reese's Peanut Butter Cup miniatures. And now I really want to go buy some Reese's Peanut Butter Cups. Don't I hate it. I don't know why I use problems with food in them, because that makes me hungry. Okay, so we are going to find my notes so I'm in the right spot. All right, there we go. Okay, so I'm going to take these. I've got 1, 2, 3, 4, 5, right? I've got my n equals 5, so I'm going to write that off to the side. Oops, not m, n. N equals 5. Right, so I'm going to add those up and divide by 5. And that will tell me my point estimate, right? So my x bar. My x bar is going to be, add those up, divide by 5. You should get 8.8057 grams when you do that. right? Just add these, divide by 5. That's what you should get. So that is my point estimate so far. Okay, next, part B. Use the listed sample data to construct a 95% confidence interval estimate of the mean weight of the Reese's peanut butter miniatures. All right, so let's do that next before we answer the rest of it. Okay, so check your requirements. Is it a simple random sample? Yes, we already know that. B, the sample size is only 6. So we have met that requirement that the sample size is less than 30. So we're good. All right, let's see. What do we do next? All right, construct the confidence interval. So first thing I'm going to do, confidence interval, I need a couple things. Now, you can do your, a lot of technology will do this for you. Like you just tell it that's what you want and it'll do it for you. We're just going to do everything by hand. I'm going to pretend that I don't have any technology at my disposal, if that's okay with you. All right, so first let's find the critical values because we need this 95%. So I need to find the t distribution for 0.025. And that's again what I just did earlier, right? We looked that up in the chart, right? And that was 2.571. I did that on purpose because I wanted to have it ready for this example. All right, so there is my critical value for this problem, again, because I don't know the standard deviation of the population. All right, so my error is going to be that critical value, 2.571. I am going to multiply that by the standard deviation of my sample. So from that sample before, you will also need to calculate the standard deviation. And that is the one place where, man, that technology comes in super handy. Okay, and that standard deviation turns out to be 2054. So this might take you a little doing if you're doing it by hand. You're going to have to go way back. We talked about finding standard deviations many lessons ago, so you definitely should go back and review that if you need to. And then you're going to divide that by the square root of n, which is the square root of 6. So I'm going to put all that in my calculator, and I get 0.215589, yada, yada, yada. Okay, so how do I find the confidence interval? I'm going to take the x bar, and I'm going to add and subtract to it that estimator. So I'm going to take 8.8057 that I found in the last place, and I'm going to add or subtract that 0.215589. All right, so I'm going to put mine in interval notation. So on the low end, I get 8.5901, because notice my mean was in 4 decimal places, so my answer should be in 4 decimal places, comma, and then I'm going to add the error to get the high end. I get 9.0213. Again, 4 decimal places, 4 decimal places. All right, so what does that mean? All right, let's get our interpretation part out at the end, because this, for most people, is the most difficult. Interpret it. Okay, we are 95% confident that the true mean value weight of a Reese's peanut butter cup miniature is between 8.5901 and 9.0213 grams. That's what that's saying. Everybody good? Right? No, it's kind of confusing sometimes. Okay, important note. Because the bag had 38 cups in it, the mean weight of a cup should be this. Okay, if I actually calculated it from the actual container containing the 38 cups. Okay, notice that our confidence interval that we found did contain this, right? This value was between 0.85091 and 9.0213. So our package appears to have been filled acceptably with the Reese's peanut butter cup miniatures. So this is why we do all this, because we want to make sure that, you know, we're getting our bang for our buck and they're not gypping us on our peanut butter cups. You can find the mu and the margin of error the same way we found them when we did proportions in the previous lesson. So find them exactly the same way. So I'm not going to go over that again, but if you need that, please go back to the previous lesson on proportion estimates and proportion confidence intervals, and you will see the same, but I'm not going to go over that again. We did that before. All right. Now, what do we do if we know the standard deviation of our population? That's when we use our Z. Okay, so you only use the t-distribution when you don't know the standard deviation of the population. If you do, then you're just going to use your z-value, and the error looks exactly the same, except you're using a z versus a t. So here's a nice little chart to kind of help you figure this out. So if it's not known, and that's the important thing, if this is not known, and it's normal distribution, or it's not known, and your sample size is greater than 30, same thing, you're going to use that t-value. But if it is known, and this is the important thing, if it is known, use the z. That's the important thing. All right, so let's do some examples, just like we did with the t's, but we're going to do z's this time because I'm going to tell you the standard deviation of the population. Here we go. So a survey of 30 emergency room patients found that the average waiting time for treatment was 174.3 minutes. Assuming the population standard deviation is 46.5 minutes, find the best point estimate of the population mean and the 99% confidence for that population mean. All right, so here we go. Since it is known, we know you're going to use z, right? So that's the important thing. So we have a 99%. So our z critical value that goes with that 99% is 2.58. And that's one of the ones I asked you to memorize because you will use 99% a lot. Okay, so let's find our error. Our error is that z value, our z critical value. We're going to multiply that by the standard deviation of the population and then divide that by the square root of n, which is 30 in this case. All right, so put all that in, and that is approximately 21.9. So that is our margin of error, 21.9 minutes. Okay, so the confidence interval is going to be our x bar, which they told us, right? Did they not tell us what our x bar is? Yep, they told us the average waiting time right there. There's our x bar. So is the 174.3, and then you're going to take plus or minus that 21.9 minutes. So I'm going to do mine in interval notation. 152.4 is the low end, and then when you add the error, you get 196.2 minutes. So we are 99% confident that the mean waiting time for emergency room treatment is between 152.4 and 196.2 minutes. Looks very similar to what we were doing with proportions, right? It's just the formula is different, right? We find the error differently, but then we do the same thing at the end. So you will find that a lot of this is very repetitive. Right? You can also use this information to find the sample size if you want to recreate a survey, just like we did in the previous section. So again, notation is the same. Again, your sample must be a simple random sample, very important. And when you need to find the sample size, this is all you need to do. You are going to take your critical value times your standard deviation of your population. You're going to divide that by the error, and whatever that is, you're going to square it. And that will tell you your sample size. Round off error is, again, exactly the same. If you have a 0.1, you have to round it up to the next whole number because you're talking about people. So always round up to the next largest whole number because you're talking about surveys or samples that you need. You can use, if you don't know when, if you don't have a known standard deviation when you're finding sample size, which that could happen, the best thing to do is just use the range rule of thumb. And we talked about that many, many moons ago, so I just wanted to add that in there, that the standard deviation is approximately the same as the range divided by 4. So you could use that for your standard deviation. But just know that. And when you start the sample collection process without knowing the standard deviation of the population, it's really important that most people just use the sample in place of the population. But again, the more data we have, the better off we are. So I'm kind of in that with. You could also use prior results. If you can find other data that showed you the sample size and that had sample size and it had the standard deviation, then use that. So you can always pull in other information if you need to as well. All right, so let's do an example. IQ scores. All right, assume that we want to estimate the mean IQ score for the population of statistics students. How many statistics students must we randomly select for IQ tests if we want a 95% confidence that the sample mean is within 3 IQ points of the population mean? All right, so again, a lot of information here. Number 1, we've got our error, right? Within 3 IQ points. That is my error. I've got a 95% confidence. Okay, so that's going to tell me my Z, my critical values that I need to find. Okay, so 95%, remember that's when you should have memorized, that's 1.96. That is my Z critical value that I need for this problem. All right, now my standard deviation. Okay, do I know the standard deviation for the population? It doesn't give it to me here. However, I can go find it. Right? I could go look that up and find what, because they have a lot of information about IQ tests. So if you go look it up, you will find that the standard deviation for IQ is 15 IQ points. That's the standard deviation of all. And there's a lot of data about IQ out there. So that's the good news, is that you could go out and find some prior results and prior information. So we're going to use all that and we're going to put it all together and find our sample size. Again, so to find your sample size, you are going to square that critical value. You're going to multiply it by the standard deviation, which we just found out was 15, and we're going to divide it by our error, which was 3 points. So take that, put it in your calculator, square it, and that turns out to 96.04. So because we have that decimal, we have to round it up. So we need 97 students. We are going to have to offer them an IQ test to get a 95% confidence interval. So hopefully that kind of straightens things out. All right, one more example and we'll call it a day. A researcher wishes to estimate the percentage of M&Ms that are brown. He wants to be 95% confident and accurate within 3% of the true proportion. Right? How large a sample would be necessary? Okay, so this goes back to proportions, right? And I brought this up because when you're reading problems, it's very common, like you just think, oh, I just should do the same thing I did in the last one. Okay, very careful. Proportion size. So this goes back to the problem that we did earlier, right, in a previous section. So N is proportion size. So we want P hat and Q hat, and we're going to, multiply. You know what? Let me make sure I write the same as it was before. So we take the Z of alpha over 2, we're going to square it. We're going to multiply the P hat and the Q hat, and then we're going to divide all that by the error squared. Okay, so it's the same formula we used last time. So 95% confident means we have 1.96 is my critical value, and I'm going to square that. My P hat. Now, P hat, do I know the percentage of M&Ms that are brown? I don't know. I don't have any. There's no error. There's no anything here. So I'm just going to use 0.5. I get a brown one or I don't. So my Q hat would also be 0.5. I get a brown one or I don't. And then my error, I want it in within 3 percentage points. So 0.03, and I'm going to square that. So I'm going to put all that in my calculator, and I'm going to get 1067.1. So that means that I need to sample. So my sample size needs to be 1068. So that's what I would need to do as a researcher to make sure that I get a 95% confidence. Now, this might change if I could go do some research and find some data on the brown M&Ms. And M&M actually used to post this data, but they stopped a long time ago. So you could use the last known data, but that might not be very, very consistent because you don't know if that is accurate anymore. It used to be, but who knows now. So we're just going to go with 50-50. All right, so again, be careful of those keywords. Make sure you know which formula to use depending on what you're working with. Again, this was a proportion problem, not a mean problem. So again, I'm just putting that out there because you need to be ready. You know, when you get tested, they might not be in a row. You need to make sure that you're reading critically so that you're pulling out the correct points and using the correct formulas for that problem. All right, so go practice. Good luck. And in the next unit, we're going to be discussing hypothesis testing. So make sure you come back.